I'll just start this one. Okay, so this is just the, the most general, in some sense, linear PDE that's a first order. Let's see, linear, non-autonomous. Right, and so we know how to solve this, or at least those who've had 438 have talked about solutions of this along characteristics. And the idea for characteristics is that we let x and t be functions, and of course x here is not x is not a scalar, it's a vector. So by x I mean all spatial components. We let x and t be functions of s. We parameterize them as some curve, and then what we do is we look at the graph of the independent variables and the dependent variables, and let's see. We look at the derivatives of u. So this might be a different way of seeing method of characteristics than you've seen before. Grab a copy of this when you have a second. But we just look at the graph. This has, if we have, say, n minus 1, if we have n minus 1, n minus 1 independent variables, spatial variables, and we have time being one variable, then this graph that we're talking about, this lives in R2n, right? And this is, what it looks like is the graph of the gradient, right, of this function with the independent variable. So another way of writing it is just saying x, counting the t as part of this vector, and then the gradient of u. And this is fairly abstract, and then the idea is that when we look at this graph and we take, say, a derivative of this equation with respect to x, and I won't go through the details because it's kind of berated in wave phenomenon and fluid dynamics and 438, but when we take the derivative of this equation with respect to x, we get the curves that are tangent to this vector field, to this graph. The whole reason I'm viewing it this way is the geometric perspective, which is much more general, allows us to do the same thing. So what I'm saying is once we have done that, we will get a system of ordinary differential equations, du ds being c, and then dxi ds being a sub I. These are functions, right? And this looks familiar to everyone, right? Everyone's seen this before? What's missing in the specification of the original equation? Well, conditions, right? Initial condition, for example. So we always do method of characteristics is applicable for an initial value problem where we have a spatial function at some specified time, say tau. Since it's non-autonomous, that's important. We could, if we wanted, just talk about it at time 0 and change this function to be whatever we need it to be for that to happen. And we call this some initial function. Again, in one dimension, this would be, a one-dimensional function. If we're talking about wave propagation in one dimension, this is our initial wave. But I'm doing this, as general as possible, and I believe it's presented this way in 438. When we have this specification, then we introduce kind of an initial time here, and for these equations, their initial conditions, such that they match up to where x at 0, right, this initial vector is parameterized, if I remember correctly, by tau, right? Is the way we do it? Those of you who are in fluids? So here, since we have I spatial components, we have I parameters here, and then we have that u at 0 is parameterized as f of tau. Is this correct for what you guys remember for method of characteristics? Is this clear? So I'm only talking about this. This isn't even in the book. I'm only talking about this because after hours of reading this chapter, or this section, I was able to see a connection between this way of viewing method of characteristics and what he does in the book. So I will start now with his section. So we talk about a fully nonlinear PDE, and we talk about it defined on some open subset of a manifold. So here, this is some open subset of a manifold. U is, of course, a scalar function from this to Rn. So U is a function from this open subset to Rn. Most of this parallels the development we've been talking about. For the coordinates in Rn here, the book doesn't do this, but it says that at our initial condition, we take xn to be 0. On xn equals 0, u is equal to some initial function. They call it v. I'll call it f to parallel this. And this is just our initial condition. It can be at any of these variables, any of these independent variables being a certain value, but without loss of generality, you can shift things around as usual to say, okay, let's select the nth component. This sort of corresponds to our time over here. And this is now kind of a surface, right, parameterized by n-1 variables in Rn. So it's sort of our initial surface, and then things move forward. Likewise, we've seen this when we graph waves. Waves move forward with respect to time. Same thing when we turn on time here, in a sense. So here's what we're talking about, and then our equation. Here's our initial condition. Our equation is just a function of this vector in Rn, the dependent variable, and then the first derivatives of the dependent variable. And this function, of course, is a scalar function of vectors, right? Everyone can see that this is a function of vectors, and it's scalar valued. So we say it's equal to 0. And it's a function of course, these two as vectors, so it's different components. This is one example of that equation. Is that clear to everyone? So I'm trying to present this in a way that's not too abstract, mostly because I don't understand the abstract stuff. Right, so the way that they actually talk about this is they say that xn equals 0 parameterizes a surface, so all of the other variables being free. This surface is all vectors, x1, x2, xn minus 1, 0. And it's just that, right, such that xi is in R. So this is a surface, and then the notation they use is u along this surface has some value. So hopefully that makes this hypersurface idea make a little more sense. Surface of dimension 1 less. Right, and everything we're doing here is local. So on a manifold, of course, you have coordinate charts, and I don't know if we've even talked about that much in this seminar. But locally speaking is what we're doing all of this with respect to. So on a manifold, we can define locally Euclidean coordinates. And that's what we've done for this entire discussion. Okay, and then they say that if we have, and we won't get into this too much because both Dr. Evermedia and I don't want to talk about geometry as the main focus, but if we view this all geometrically, and they say that they will prove later in the book, I'm not sure when he gets around to that, if we assume a Riemannian metric, which means that metric of certain properties, then we can associate with the gradient of a vector the differential form of that vector, right? I'm not sure if this makes much sense, but what this allows us to do is, like I've sort of talked about the geometric perspective of this, linear first-order equation, we can talk about it geometrically. In this case, without even talking about manifolds or complex geometries, we can also talk about a fully nonlinear system, just like this one, except we're talking about Rn to Rn. And we can do that geometrically. I'm talking here about graphing this surface this way. If we graph it that way, then this being the independent variable, this being the dependent variable, right? And this surface is graphed in R2n, right? Because it has 2n independent components, and it has n independent components and n dependent components. Well, the curves that are tangent to that surface are the integral curves of our equation, etc., etc. And geometrically, that allows us to define this system of ordinary differential equations. And that's kind of powerful and useful, so differential geometers and people like Michael Taylor over the last 100 and some years have viewed it this way. I'm not sure who first came up with this, but if we view everything differentially, if we talk about this equation, where we have this differential form as part of the equation, and this is the object we're studying, well, first he says that we're going to talk about an equinal equation, which is where it's not dependent on the variable u. Likewise, if you look at the equation I have written here, there's no u dependence. We can discuss the method of characteristics in terms of the quasi-linear case when there is u dependence, and normally when we discuss method of characteristics, that introduces a lot of complexity, etc., etc. So likewise, he begins with the equinal equation, if I'm pronouncing it correctly, which is just saying that this is a function of the dependent variables and then this differential form. And what we are looking for is a graph of this du in, what we are graphing is the function du in the space R2n. And really, he calls it this lambda. And lambda is a graph of du in this space R2n. And then what he gets into, and what Dr. Avermedia was mentioning to me when I talked to him, is the connection between this kind of equation and Hamiltonian systems, right? If we remember, and I'm not sure how much we did in the seminar, but that du can be written this way. Let me make sure I do this correctly. So as du, I'm trying to remember what goes here. Is it du dxi? Is that what I'm thinking of? Yeah. Yeah, so this is the differential form corresponding to u. And it's a differential form, of course, because of this component rather than a vector. So we can associate it this way. And if we call these objects momentum, right, which is what we've been talking about, ignoring all of the details that are covered in courses like methods of mathematical physics, we associate with these momenta, I believe covariant vectors should be down there. Then what this is the graph of is this is the graph of my vectors or the graph of my momenta with respect to my vectors, right? And everyone knows what I mean by a graph of a function, right? You've seen the notation if I have x and f of x, and whatever, dimensions these are in, you add them up, and this is a graph in that dimension. Everyone has seen this notation before? So it's the same thing. We're graphing the momenta with respect to the independent variables. Both of these are n-dimensional vectors, and they have some properties, of course, because I've said, and this graph, this lambda, is of the initial condition. It's the initial space, kind of like we were talking about over there. It is a way of expressing this S, if I have my idea correct. So that means that the nth component here is, of course, 0. And then we also have to say, I believe, that one of the conditions for all of this to work is that the nth derivative of u, that nth component of the gradient, is not equal to 0.